Yes, and the next topic is file level replication, and where is he? Here. And I present you Jinshan.
Okay,
Please.
thank you, Mike.
Jinshan.
Hi.
Thank you.
Thank you.
No, really, thank you.
Okay, so yeah. Okay, so actually for Mike's question, okay, so you can set a limit, on the file size on data MDT. So if when the file keeps grow, right, and it is over the limit, and the new layout will be created on the OST. So the bytes after the limit will be stored on the OST. So basically, you will have a file, part of the file is on the MDT, and the rest is on the MDT.
Right, in phase 2. So I was curious about phase 1.
Oh, so actually, I guess this must be done in phase 1. So for phase 2, it will be automatically migrate the for example, 4K bytes on the MDT to OST automatically, right? But in phase 1, you have to run a command tool, for example, to migrate the bytes on the MDT to the OST. Yeah. Okay, you're welcome. So, I'm going to talk about replication, and my last name is Xiong. Yeah, Xiong. Yeah, not Xiong or Zion. Yeah, it's Xiong.
Thanks.
You're welcome.
You're so polite.
Sorry, so I'm just a little bit nervous. Okay.
I would thank you for being polite, but you might say you're welcome.
Okay, so I'm going to talk about replication. So there are 4 topics will be covered in today's presentation. So first is what is data layout, and then which data layout will be used by replication. And then I'm going to go over what the replication will do, why to bring to Lustre. And then I'm going to dive into the implementation a little bit to talk about the IO model for replication. And then I'm going to wrap it up, by talking about the current status for the replication. Okay, first of all, so what is data layout? In case some of you don't understand what is data layout. So data layout essentially control the data placement on OSTs. So it is stored along with MDT objects as an extended attribute, which will be interpreted at LOV layer, to control the data path. So if you can, see the diagram, the red lines are data path, so which is controlled by the at LOV layer by the data layout to reach the right objects on OST. So data layout used to be immutable after setting, so you can't change, your data layout later on. So we're going to change this. Okay, so the current data model in Lustre, so we can only support read 0, that is striping right now. So it has some major drawbacks. For example, the file is not accessible if any OST failed. And also, if you want to increase the stripe count, you will decrease the IO availability. Why? Because if you have more OSTs for a file, the chance of one of them, will be dead, right? The high opportunity for one of them will be dead. So, even worse, if you have disk failure for one of the OST, and you cannot find your data back, you will just lose them. So obviously, you cannot deploy Lustre on commodity hardwares, because of higher failure rate. Of course, it is not suitable for cloud computing environments. Okay, so for the data layout for replication, we're going to invent RED 0 plus 1 for replication. So basically, essentially, we're going to store, multiple copy of the same data in the cluster, just replicated multiple times, and each copy of data is called a replica. Each replica can be represented by individual RED 0, right? So this way we can, easily to operate replicas. For example, it would be very easy if you append a new replica to a current existing replicated file, or you can, just simply take one replica out of a replicated file. And another advantage of this way is we can reuse, the current code as much as possible, right? Because we have very mature code for RED 0 support. Okay, so I'm going to talk about replication. What the replication will do for us for Lustre. So the biggest advantage for replication is to improve I/O availability, right? So if one replica is out of reach, it's available, so we can change the I/O engine to get the data from other replicas. So, this is actually a very good a very cool feature for Lustre. So, as you may know, Hadoop, it has very good I/O availability, right? Because you can store 3 replicas in the cluster anytime, right? But Lustre itself is another extreme, because it can provide you lightning fast I/O speed, but there's no any data redundancy. But there's nothing in the middle, in between. So replication can actually address this market by providing reasonable data redundancy, and at the same time provide very good I/O performance. So, this may open a gate for Lustre to enter into enterprise market. Yeah, really good opportunity. So after the replication is done, you don't need any expensive data storage for OSTs, and it is not necessary to configure HA, right? High availability. It can also improve read bandwidth. So essentially, you can have multiple copies of the same data distributed in the cluster, and different clients can actually pick different replicas to read, by some policy. For example, topology information or a type of OST, etc. So for a real use case is that if you are going to use Lustre for virtual machine deployment, this will be a very good target for replication, right? So you can start up, thousands of VM instances on the same time, and you don't have to, different clients can read the same VM image from different replicas. So the starting up time will be shortened. Of course, replication is not free, so write will become really expensive, and which I will talk about later. So basically, replication is good for read most, but write rarely files. So the design is funded by OpenSFS. So yeah, thank you very much.
You're welcome.
Okay, so let's dive into the I/O model for replication. Okay, so read to replication. So in the past time, you don't have any choice to read a read zero file, right? So, but right now you have so many replicas. So there will be a policy to run on the client side to pick up a replica to serve the read request. As Andreas mentioned before, ideally, we should add topology information into OST, right? For example, rack information, server information, but this will need a lot of work. So we can take advantage of OST pool here. So you can create, different OST pools by topology information. For example, you can create one for OSTs in one server, and you can create another one in one rack, and you can create the third one behind the same switch. So basically, you have to isolate the failure, right? So for example, if one server down, you don't want different replicas locates on the same server. So there actually will be two policies for replication, one on LOV layer for read, and another one on MDT for write, which I will talk later. And there will be a retry mechanism. So I/O won't be waiting at OST port RPC layer at what we do right now. So if a specific OST is unavailable, so after a retry mechanism is introduced, the I/O will be failed immediately. So the upper layer will be notified for this failure, and then I/O will be reissued. And then at LOV layer, the policy will pick up another replica and then to reissue the I/O. Okay, so write to replicated files. So write is very difficult because data consistency is the last thing Lustre can sacrifice. Actually, I made a proposal, before to just a different solution for replication, but it can sacrifice the data consistency, and which is immediately killed by Eric. So why write is difficult? Because node can fail at any time during a write. So it will become extremely difficult to maintain, the data to be exactly the same among replicas. Another problem is phantom writers from evicted clients. So as you may know, we met some big problem for this for Xiong MDS project. So we're basically facing the same project, but I'm going to solve it. Okay, so the two-stage write we come up with a two-stage write for replication. So basically, we're going to pick up a replica as a primary for write, and then we're going to mark others as invalid. So during this time, the replicated file is degenerated as a regular file, right? So we don't have to maintain the exactly the same copy of data, all the time. And after the write is done, we're going to initiate a asynchronous data copy from primary replica to stale replicas, and then we can bring the stale replicas to be valid again. Okay, so this is a diagram for two stages write. So the picture on the left, there's a read-write request, and we have a read-one layout. And for this specific file, it has 3 replicas, and replica 1 is picked as the primary, and replica 0 and 2 is marked as invalid. So read RPCs cannot go to replica 0 and 2. Yeah. So after the write is finished, okay, so the diagram on the right, so there's no read-write request. And there's nobody opening this file for write. We can start a resynchronization process. So the data will be copied from replica 1 to replica 0 and 2 asynchronously. And after the copy is done, we can tell the MDT that we have valid data on replica 0, 1, and 2, so you can mark all of them as valid. Yeah. So after this is done, and you have a complete replicated file, and each replica can serve read request. Okay, so a version replica is invented to address phantom writers from evicted clients. So essentially, we add a version number to replicated file on the MDT, and this version number will be transferred to each replicas, essentially the OST objects, right? And stored in the permanent disk. And the version number will be distributed by the open request to client. And for each write RPC, it has to carry a version number, and the write can succeed only if the version number in the write RPC matches the version number of replicas. Yeah. So this is the whole idea. So let's take a look at the diagram. So there's no. Okay. So first, this is the resynchronization clients. It was sent a resynchronization request to the MDT, and then the MDT will increase the version number, and then transfer the new version number to the OST. After this is done, the resynchronization client can start data copy, and after this is done, the resynchronization client can notify the MDT, so MDT can bring stale replicas to be valid again. So during this time, if an evicted client tries to write replicated file, the write will be denied. Because why? Because the evicted clients will not get the notification of version number change. So you basically use a old version number to try to write the new replicated file. So, the OST will simply deny the write request. So, so another benefit for this is that we can revisit the feature of SysOMDS and make it work like this, really easy. Okay, so the current status of this project. So again, this will be a two-phase project, and phase one is to provide basic functionality. For example, replica read, replica write, and resynchronization tool. And in phase two, we are going to address the write performance. So we are going to invent immediate write, to write different replicas on the same time. So the HLD has been finished for phase one. As I mentioned before, the HLD was funded by OpenSFS, so thank you again. Okay, so we still need funding for implementation. So, as I mentioned before, this is a really good feature for Lustre. So, if you want to fund this project, it will definitely accelerate the progress of it. So, if you think this feature is really important for your product, just please contact with our management team, for funding. Okay, so yeah, that's all. Thank you.
Thank you.
Yeah, please.
So have you ever thought about using erasure codes instead of making duplicate copies? I mean, for HPC with large file systems, making an extra 50 petabytes just to copy something there is very expensive, and I don't think we'll do it.
Well, so, yeah, basically for HPC use, for HPC use, the application just dump a lot of data, to OST objects, right? So essentially, it can never read it back, unless some node failed, right? So you have to read them back to start, to read the last checkpoint and start all of your work again. So yeah, so I agree. For HPC, you don't have to use replication. But for other market, replication means something, yeah.
Worth mentioning that the layout is per file, right? So you don't have to replicate
Oh
all
yeah, thank you. So yeah, so the layout is per file. So yeah, so this is why we do have a file level replication. So for example, if you have a log file, right, which is write quite often, so definitely you don't want to set up replication for it. But you have a configuration file. Yeah, it would be a very good idea to have, multiple replicas for the file. So did I answer your question?
Hey, Jinshan. I just wanted to extend the conversation a little bit about whether HPC could use this. Some of the work that Katie Antibas and I did at NERSC back in my previous incarnation showed that, at least on the systems there, the reads were actually greater than the writes. We actually did 1.7 times as many reads as writes. And that comes, I think, primarily from like chemistry applications, maybe some genomics. So there is actually a place for read many times, write less often.
Oh.
And so obviously, you'd want the feature to be optional so that you don't have to have every single, core dump all of the things that get written and never read shouldn't be replicated, obviously. But if it's an option, I think HPC would actually have a place for it.
Yeah.
Yeah, so a quick question on the, when you invalidate the replicas, are you doing the entire file or is it extend space? I mean, if you have a 1 terabyte file out there and you update 4 kilobytes in the middle, do you have to what do you have to replicate? How does that work?
So actually the replication is for the entire file, but I mean, you mentioned a good point because, this is something we can optimize, right? So, for a several terabytes file and only 4K is updated. So you don't have to copy all of the whole file. So you may just copy, portion of it. Did I answer your question?
Yeah, you answered the question. I just don't like the answer.
Okay.
Is there are you planning to have a mechanism so that if I'm monitoring my OSTs, I can tell you that this OST is about to die and not to use it as a primary or to take it off the list?
Yeah, of course. Yeah.
If OST goes down, so suppose we have 2 replicas. One OST goes down and I retired it. Now I have 1 replica. Is it going to be automatically replicated? And second question, how do you control data integrity? If file is replicated several times and at some point it was bit flop and data not valid anymore in second replica, and that can be propagated to future replicas. So first question, do you have automatic replication when OST is retired? And second question, if you have automatic replication, how do you control data integrity?
So actually, you are making some advice instead of questions, right? So can anyone repeat his questions briefly? Okay.
So I think I can answer some of those questions. So when a file becomes stale, like a replica becomes stale, the current implementation is that in phase 1, it gets logged to a change log, and the rate at which you re-replicate the files is a policy that you can set. And there's going to be a simple tool that just reads the change log and re-replicates it. But it could be integrated with something like Robinhood so that you have different policies depending on the tree or the file type or the user or whatever you want to how quickly those files should be replicated, right? It's also worth mentioning about the 4 kilobytes in the middle of a 1 terabyte file. The files are only going to be marked as stale in the initial phase 1 implementation. In phase 2, the typical operation is going to be that if you're writing to a middle of a file, all of the replicas will be updated. And only in case of an OST crash while you're updating your file would there need to be a resynchronization later on, right? To answer your last question about data integrity, if you use something like ZFS, the backing file system will have data integrity and it'll give you an I/O error if you try to read it after a bit flip. And there is just the beginning of some work for ext4 to also add data checksums at that level. We haven't done any work or planning to do data integrity, between replicas at the Lustre level, but it would be possible depending on what your resync tool is doing. It can compare the replicas or something like that.
Okay, that's all we've got time for. Jinshan, thank you.
Thank you.